I stopped you from going into this before. So why don't you go into this now?
Mm-hmm.
How do these same observations work on the flat Earth model? Do you have a flat Earth model that you're testing these against, or talk to me about that?
Sure. Flat Earth model is simple. What's the line of parallel? In other words, what's the limit for the flat Earth model? So when I look at the 45-degree sector test, now you'll see on my website, I use the test box. So when you look at both of the models, you'll see numbers in there.
Okay, I'm looking on your slides. Can I show that?
Yeah.
Let me share.
Just go to it's right past, I think, number 4.
2, 3. Timing. Sun clock 4. You want 4 or past 4?
Right
Test
past
box.
4, right there. So you'll see these are both models when I looked at testing them. Okay. So these are going to kind of give you your limits. Now, in the 45-degree sector test, off a flat model, are you going to ever reach that limit? In other words, that limit, you'll see a 90 degrees on there. You're never going to hit that. In other words, that is such a high bar. Now, is it actually 90 degrees? It's actually 87, about 87.6. And the reason I say that,
what are we talking about here? There's a subsolar point on the flat Earth model as well, right? And at the subsolar point, you're still at 90 degrees, right?
Yeah, but you see in the flat Earth model, your sun is a lot smaller. So your sun is between 50 and 70 miles wide. In other words, you have to understand line of parallel. In other words, on the heliocentric model, you've got this huge sun.
Yeah.
Okay. You have to remember your height measurement is a measured alignment. So in other words, once you come off or once you exceed that line of parallel, you ain't coming off that model. That model's done. It goes into geometric failure. So now the flat Earth model, you would have to get up over 85 degrees, about 87.
Can you show the math? Can you explain to me where you got 85 degrees? Are you talking about 3 hours later? 3 hours after local noon?
Well, you take the sun size, and the sun size ranges anywhere between 50 and 70 miles. Now I have it at right about 69 miles.
Okay.
That's something that needs continued study. That's going to be about at between 3,000 and 4,000 miles. That's going to be about 2.4 degrees. So in other words, we do a fan. In other words, when I talk about a fan, we do an area. Okay. So you're talking about a sun that is somewhere between 50 and 70 miles in size. So your line of parallel is you're actually going to have a line of parallel at about 87, up past 85 degrees.
I'm super confused. I don't see how the size of the sun is related to its position.
Oh, yeah, absolutely.
We're saying, let me the flat Earth model that you're working with, is it the AE map model? Where
there's a
picture. The sun goes around.
Yeah. There's a picture on there, Matt. Keep going down through it. Right there. So
the sun circles overhead. And so you're saying that the subsolar point moves around at a particular latitude during the day.
Yeah.
So
like a record player.
So 3 hours. So 3 hours later, it's over here.
Yeah, that's your sector. That's both models. So
now, how did you come up with the fact that would be 89 degrees?
You mean 87
or 87 or whatever number? How did you come up with the number?
So all you do is you're going to
math, and that's not what I got.
you're going to look at your fan or your distance at between 3,000 and 4,000 miles is going to be about 2.4 degrees. And an object that's going to give you an object size of about, I have it right at about 69 miles.
I see.
So we say in the community, your sun's between somewhere in the neighborhood of 50 to 70 miles in diameter. And all that does is it moves. So you're going to have to get up past 85 degrees to exceed your limit. Are you ever going to do that at 10 o'clock or between 9 and 10 and 3 and 4 in the afternoon? No.
Okay.
You ain't
So
got a long way.
I think I do get this now. I think I get this because I've never seen that particular number, because on the flat Earth, it varies depending on where you are. The sun
distance.
The sun arc rate is totally different depending on if you're, you know, north, south.
That's why. And I talked to one guy up in Canada. He was talking about the North Star, and he goes, "Well, I don't know how people can think the Earth is flat," because he talked about the North Star, and then he had these positions from Cuba and a couple other places he was doing triangulation. I said, I just put a protractor on it. I said, well, what angle can't you get from here on a flat surface? It's less than it meets the line of parallel. So I said, flat surface is too easy, Matt. And people,
it is very geometrically easy comparatively. So let me posit at you. You know your latitude and longitude. You can plop yourself down onto this map, which looks like you're kind of doing. You could calculate, based on the height you think the sun is above the surface, exactly what altitude angle, elevation angle you should get for the sun. And you did calculate that, and you got like 89 degrees.
Yeah, you can. That's the limit. In other words, that's a limit. So when you take those measurements that I took for like resolution time, when I send you, you apply those to the flat Earth test box. They're all within limit. They're within that limit. Do they meet that height standard? Yes, they do. On a flat Earth.
When you say limit, what establishes the limit for that?
Again, you have to get up above 85 degrees. In other words,
okay, let me rephrase. The lower the sun, if the sun is lower or higher, because you don't actually know the exact height, right?
Well,
depending on how high above the surface the sun is, you're going to get a different angle, right? Right?
And yeah.
And so is that the limit you're talking about? It's saying like, oh,
no, your limit when you're looking at something, okay, when you're shooting an angle, okay, this is what gets heliocentrics in trouble. When you come off, because that survey point, you're pinned to it. In other words, you can't come off that survey. So when you elevate up and you measure up, if you look at your angle, remember, you're always center mass of the sun when you're looking at it. Okay. If your angular measurement, when you do your math, okay, when you do your range fan, if that exceeds, and that's why you'll see range fans down there for right triangle. This is the same as this would be the same as a safety artillery impact zone. If that exceeds your fan, you're off that model's sun. You're no longer looking at it. So
what if it's too low? But what if it's too low? Wouldn't that be a problem too? You need to have an upper and a lower limit.
No.
Why don't you need an upper and a lower limit?
Because you're at 0 degrees on a flat surface. You have a full almost 90 degrees to measure that. What angle can't you get?
It doesn't make any sense to me. I can get any angle. What I want to know is, where is the sun? The sun should be at one angle. The sun is at one angle at any given moment.
Right. So when we get up, and I look at the prime meridians, when we look at the equatorial plane, I think the sun will be close to 60 degrees in that 45-degree second. If you're linear east-west, I think it's going to get close to 60, because we're already like North Carolina here. I got over 52 degrees on a westerly read.
Yeah, you would.
So if you get more, and remember, do you understand when I say more linear east to west?
So no, I don't really know what you mean.
If I come into my location, the OS is in the equatorial plane. Okay. Because if you look at my sector, and it's both for both models, that fan is east to west. In other words, I'm going to measure from my start point where I put my survey 3 hours later. I'm going to measure that sun in its position. So,
the sun moves from east to west,
right,
throughout the day.
And then your easterly read is going to be the following morning at 9, if your solar noon time is at noon. So it's going to be at 9 a.m. the following morning.
Okay. Well, that definitely brings up a follow-up question which is I'm still very unclear how you're calculating your numbers. Well, let me just stick on this first. Are you using trigonometry to calculate these limits? How are you calculating this limit?
So go up and look at your range fan.
Which is number... That. Is this it?
No. Keep going.
This one?
Okay, go back to that one here.
That one.
All right. So now, when you say I don't understand how you'd get that, look at that diagram and tell me what you think you see.
I see you showing that as you get closer to directly underneath the sun, the angle increases.
Okay.
And the farther from directly underneath you are, the angle decreases.
Okay. And now we have the subpolar plot. That's what I call, or I define as the guide angle. That's the flagpole angle. In other words, that's your 90-degree line. That's your first line in the line of parallel. Okay.
Right.
So when you make your measurements, if you look at that elevated object, okay, if you were to continue to come up off that object, in other words, on a flat surface, okay, you would have to hit almost about 87 degrees. Then you're going to start to come off the small sun, as you're coming off it for the flat Earth model. So
I'm not seeing where you're getting 80-something degrees.
Well, because
unless you've plugged in particular numbers. If you plug in a number for this height, and you plug in a number for this distance, you can get different numbers, right?
Well, of course, yeah.
Okay, so did you have a particular height you're using?
Yeah, when we talk about the sun size in the flat Earth models, the sun is very small, so you're going to have a very small fan. In other words, it's closer, but it's smaller. Okay?
Right. So I've heard 3,000 miles. Is that
between 3,000 and 4,000 miles? Again, it's where you take that measurement. Okay. Now, to get it accurate, to get perfect, you'll have to be within that the tropics. You could get an exact measurement if you're within the tropics. You're going to get a more accurate measurement.
Okay. So when you say the limit, you say the limit of 80 whatever degrees,
that's going to be.
You're talking about this 55-degree angle would be a limit of like 80-something. So, really close to directly underneath it. Right? Again,
so when we look at your house, if you take a light in your house, right? When you look at it, okay, because it's an elevated object, okay? So you can look at that object. The farther you get away from that object, it's going to your measurement's going to decrease. So the flat Earth model has a huge advantage. I mean, when you talk about height measurements, you're not going to exceed that model unless you got up into the mid 80s. When you get up above in the higher 80s, then you're getting close to that model's limit. Why? Because that sun is smaller. That object, the sun, what you're viewing in the flat Earth model, is a lot smaller. Okay. So your parallel, or your line that is going to exceed that ball or that sun, you're going to have to hit about 87, 88 degrees.
Okay, let me ask you this. How would you respond if I said you'd use arctangent? You'd say the angle is the arctangent of the sun's elevation divided by your distance from the subsolar point.
Yeah, I'd have to see the mathematics, because in actuality, when we look at sun height measurements on the flat Earth model, if I take all these measurements, do they measurements work with a flat Earth model? They do, easily.
I would say they do not. And I'm going to use math. I'm going to use the arctangent and say that it doesn't work. Furthermore,
explain that. Explain why you say it doesn't work.
Well, you tell me the height of the sun, and you tell me your distance from the subsolar point. Calculator, I'm going to punch up arctangent and tell you this angle. And that will be the angle that you're predicting.
Let's
would
just
only be 80 some odd degrees if you're very close to directly underneath, as you can even see in this diagram, right? When you're 3,000 miles away, when you're 3,000 miles from the subsolar point, that's 45 degrees, right?
What do you mean?
If, you know, the 45 degrees is when the two sides of the triangle are equal in length. So the height is 3,000 miles. So if the ground trace is 3,000 miles, then you get, that'll be right here, 45 degrees in between these two measurements.
Well, you have to use a fan. In other words, if I take an area and I look at like my ball size, what's the size of that small sun? The ball size we're looking at between 50 and 70 miles. That's going to be about 2.4 degrees. So in other words,
the sun is half a degree across, right?
Say again?
The sun is half a degree in visual angle.
For what?
0.53, I think, for always. Is that what you're talking about? When you said it's 2 degrees, I'm not sure where 2 degrees is coming from.
In other words, that measurement angle, if you shot a line up at the sun, okay, you would have to exceed that line of parallel. In other words, for that smaller sun, you would come off that model sun.
Okay.
In other words, you're no longer looking at its center mass.
Let me ask it pretty blunt. Are you using mathematics for this?
Sure.
Trigonometry.
Look at your fan.
Let's use the trigonometric words. If we're using math, let's use the proper words. Tangent, sine, cosine, right?
Let's use...
I mean, we could just use a protractor too. You can just draw it like this and just use a protractor.
Yeah, no. Well, that's easy because if you
But the size of the sun is not part of it. The distance to the sun, the size of the sun is not part of this diagram. The distance to the sun is important, though.
Oh, the size is also important because you're talking about a linear line of measurement from a surface, whether it's curved or flat. So those red lines are your measured.
You're measuring to the center of the sun, right?
Yeah, you're always center. But you need to know,
so if it's big, you're measuring the center of a big ball, and if it's small, you're measuring to the center of a small ball. What's the difference?
But you have to. Well, your line of parallel is going to be different. Look at your at your data on number 17.
17.
Right there. Go to the top one. Up just one more. So now. At 1 degree in the heliocentric model, you're 1 million past line of parallel, you're 1,638,664 miles off that object. In other words,
you're talking about the edge, measuring to the edge of the object, not to the center of the object. That's my confusion. So I thought you were only measuring to the center of the object.
That 1 degree pulls you. In other words, that would be a total composite of 91 degrees. That's what happens when you get a measurement of 46 degrees. You're 1 degree past line of parallel. That's at 1 degree at that sun's distance. Now remember, this is an exact measurement. So now you're 1 million, you're over 1 million miles off that sun. What's the sun size? Now we need to look at the sun size. Remember, we're using half sun. Now it even exceeds the full sun width.
Okay.
So you can't be looking at that object.
Okay. I get you. I wanted to go back to this one real quick and just make sure we're clear on something. If I was standing here at the 55 degree person.
The only reason that I use this, and this is just to show that distance, you're going to get different angles. This has nothing to do with the sun size.
No, I'm not talking about the sun size. You're not measuring the sun size.
Yeah, because the heliocentric guy that I was talking to in a conversation, he didn't understand this. I was like, you don't understand if you get farther in distance, you're going to have a lower angle? He's like, well, you need to define your terms.
I can't speak for the person you were talking to. I wasn't there and I don't know him.
Yeah.
But I will say
that's the
the
reason.
way you talk about it is very confusing to somebody like me.
Yeah,
Because your vocabulary is not the same as my vocabulary.
Yeah.
So
I get
we have to go through this and struggle through what do you really mean?
Yeah.
And then we can get to an understanding.
Yeah. I understand that.
So when like what I'm projecting that I think he's talking about is if you raise this sun, you just leave everything alone and just pull the sun up, this angle will get larger.
Well, it wouldn't matter because again, you're talking about.
No, I'm just saying that's just the facts of the diagram, right? It'll get closer and closer to 90 as you pull that sun farther and farther up.
Well,
and as you pull the sun down, it'll get lower.
No, as the observer gets closer, okay, that angle is going to increase. That's what this slide is about.
True, but we don't actually know the distance to the height of the sun.
Okay, so let me ask you something. When you look at this diagram, what do you see? What geometric shape do you see?
Triangles.
Okay, now let me ask you the next question. Is the sun inside or outside the triangle?
It's at one of the vertices of the triangle.
Very good. Okay, so now you're basically within that triangle. You're connected to it.
Yeah, the observer forms one of the vertices of the triangle.
Next question is, can you shoot an angle over the top of the sun? Yes or no?
Sure.
Okay, now that object, you're within that triangle. Got a problem.
What problem?
What's your problem?
No problem. No problem at all. I can definitely shoot an angle over the top of the sun.
What's your problem?
Don't have a problem with that.
What's your distance?
Well, what I was trying to get at here is in this diagram, if you were to just imagine the sun is higher than you drew it, right? What if the sun is higher? What impact would that have on your numbers? It would increase all the angles.
But it doesn't.
No, it does. If you raise the sun, if you raise the object higher, your angle to it goes up. Simple. If you lower the object, it goes down.
Matt,
you can work backwards. Now, hold on. You can go backwards and you can say, if I know the ground distance to this point, and I know this angle, I can tell you this height. This height can only be one number. You understand that? You agree with that?
You're talking about, again, you're talking about that sun is within the triangle. So when you say
the vertex of the triangle,
when you talk about, well, the sun can go higher, Matt, the sun is at a position in the sky at a certain time of day. We ain't talking about the sun going higher.
No, we're not understanding. Let me try and explain it in a different way. Let's say I put in that the sun is 3,000 miles above the surface. And these are my angles. From that, could I tell the distance to the subsolar point?
The sun from there? Sure. You're a fan.
Okay. What if I said, no, the sun's not 3,000 miles up, it's 4,000 miles up? That would change this distance.
Well, that's based on, again, observer position. So you're going to get different calculation. In other words, you're going to get a different number based on how your calculation, your distance. So your number is going to change. That's why I said you got to be to get an accurate, you'd have to be right in the tropics. You'd have to be right in the tropics linear.
Well, I think my whole point is that this whole diagram is predicated on knowing the height of the sun above the surface.
Oh no, this diagram is just to show that an object, as you move closer or move away from it, the effects of your measured angle, higher and lower. That's it. That's the only reason that this diagram exists.
Okay.